Okay, all right. So I have this graph drawn here, and you can see that it has, would you guys agree there are some discontinuities?
Yeah.
So the question is, removable versus non-removable, right? So let's start with the easy one. Let's start with removable. Who can identify a removable discontinuity? And guys, I'm going to write DISC for discontinuity. Who can identify, and identify, just tell me the location of the removable discontinuity. Yes, Cooper.
The 1 and 4 one.
1 and 4. You mean the point, the x value of 1 and the y value
No,
of
the x value of 4 and
Oh,
y value.
so the location would be 4, right?
Yeah.
Okay. So Cooper is saying that there is a removable discontinuity at x equals 4. Okay, would you guys agree that that is a removable discontinuity? Okay, got really quiet. Do you guys think that that's a removable discontinuity?
Yeah.
Raise your hand if you were like, yep, that's a removable discontinuity. Okay, put your hands down. Raise your hand if like, I'm not quite sure if that's a removable discontinuity. Okay, good. All right. So harder question. First of all, he is correct. Harder question. Why? Why is that a removable discontinuity? You can give me a calculus answer or a non-calculus answer. I don't care. Yes. What's your name again? Evan.
The line on the left, it continues going to infinity, so it'll eventually cross that.
Okay, so we're talking about right here when x equals 4.
Yeah.
We're talking about this point right here. We're saying that that's a removable discontinuity. So what are you saying?
I'm saying that the line on that's to the left of it is going to continue going. It'll never touch. Never mind. It's never going to touch 30, so it won't matter anyways.
James?
By defining it, it makes it continuous.
So you're saying you could define a value there that would make it continuous?
Yes.
So he's saying it's removable because we could fix, I'll say quote, fix it by saying, well, I could say this. I could say g of x is equal to f of x for all x not equaling 4. And then I could say, guys, can we just pretend that that's 1? And then I could say, so question, did I fix it? Now that's f of x over there, correct? That's the function f. Here's a new function I'm defining, g of x. Guess what g of x looks like in terms of f of x everywhere where x is not equal to 4? It looks exactly like it does right there. But at 4, what have I now added? One single point. And let me go ahead and draw you that point. Let's do it in red. I'm going to draw the point. Did I just make it continuous at x equals 4?
Yeah. Can you do that? You can just add a point.
You can. And what I just did is I removed the discontinuity. I've just removed the discontinuity. Okay, so that's James' good point, pun intended. So he just told me why. He gave me a good answer why. Now, harder question. Am I going to allow you to, on the quiz, to say you could fix it? So now my question is, why with calculus? Why is it removable with calculus? And let me first start by showing you why. And by the way, we're talking about f right now, correct? So I'm going to undo what I just fixed. Okay, so that hole's back there, right? So that's a removable discontinuity. Would you guys agree that I could say that it's a discontinuity since f of 4 is D and E? Would you agree? Since f of 4 is D and E, it's a discontinuity. Why is it a removable discontinuity? What's the only calculus thing we've talked about thus far this year? Limits. So it's a limit answer. Can anyone tell me anything about a limit right there? What is the limit at x equals 4? Correct. And that's your answer. That's why it's a removable discontinuity. Now let me make this point, pun intended. This statement right here, I'm saying that the point isn't there, correct? Therefore, the function is discontinuous there, agreed? There's a hole there. There's a point that's missing. However, when I write the statement that the limit of f of x as x goes to 4 is 4, oh, it's not 4, sorry, it's 1, right? Sorry, you're like looking at me, Mr. Ryan, you just said it was 1. It's 1, correct? That's telling me that all the predicted y values are going where? To the same value. Now, in case you're like, okay, I think I kind of understand, but I'm not quite sure I completely understand. Let me explain to you a non-removable discontinuity. Would you guys agree that x equals 5 is a non-removable discontinuity? It is. See, a second ago, James said, hey, Mr. Ryan, you know what? You could fix this removable one by putting a point here, right? So here's my question. How many points would it take to fix this one?
1. Whatever's between the two.
And we probably need to have this discussion now sooner than later. Okay, you see this segment right here? Segment AB? How many points are on that segment? Infinitely many of them. Did you know that? Infinitely many of them. Oh, by the way, you see this segment right here? Guess how many points are on that segment? You see this segment right here? How many points are on that segment? Which one of these has more points? You can't really answer that, can you? So there's some stuff that goes on in math that maybe isn't going to make you feel very good. But here's the thing. If I have a line and I have this hole right here, how many points are missing? 1 point. How big is that point? It literally has no size. In fact, if I were to draw it, you wouldn't even be able to see there was a hole. But there is. It's just that one value, that 1 point. Anyways, let's go back to this. This is a hole. We can fix it. Guess what this is? It's a jump. Or you could say it's a gap. Or you could say, I don't know, a chasm or something like that. That gives you the idea that you can't fix it. The only way you could fix this gap, guess what you'd have to do? You literally have to grab this line segment right here or that ray, and guess what you have to do? You'd have to change the whole function to make it fixed, right? The only thing I needed to do to fix this guy here was all I needed, like James said, just to find the value there. So that's what I did. I left it up there. Does that kind of make sense?
Yeah.
Removable, we can fix. Non-removable, we can't fix.
So if it's just one hole and there's no like jump or anything, then it's removed.
Correct.
Okay. That makes more sense.
Okay. So you've already,
Yeah,
when
well,
I ask at the end of the period if you've learned something, you're going to,
Yeah.
Yes.
So how can you tell that if you're just given like the function itself and not?
Yeah.
Great question. Great question. That's section 1.3. Can I come back to that in a minute?
Yeah, that
Okay.
makes sense.
Now, hold on. So here I said, what was the calculus reason that this was removable? And I told you this was the answer, correct? Now let's go to that non-removable one. I'm going to erase this, okay? And let's go here. So y is x equal 5 non-removable. Why is it non-removable? Well, it's a gap, right? But what's the calculus reason? Oh, by the way, can I say that f of 5 is D and E here? Nope. This is not a true statement now. What is f of 5? It's 4. So you can't even say that to say it's a discontinuity. Why is this a non-removable discontinuity? James?
It's because the limit is D and E.
Correct. In fact, this right here takes care of both things. This is why it's discontinuous and also why it's non-removable. Think about it, guys. What does a limit tell us? A limit's telling us that it's going to some y value. They're both going to the same y value, correct? You remember, look here, like last week, I would have said something like this. As the little ant's getting closer and closer from this side, it's going to 1, right? Correct? As the ants come in from this side, they're getting closer and closer to what? 1. So therefore the limit is 1. Does that make sense? They're going closer. They're going to the same y value. It's a predicted y value. But up here, let's do green, as I get closer and closer from this side, what does it appear they're going to? So over here on the left side, they're going to 3. What about the right side? They're going to 4.
So it's everything between.
Does 3 equal 4?
No.
That's why the limit's D and E. We can't fix it if they're not going to the same place. Because there's an infinite number of numbers between 3 and 4. How many numbers is there between 1 and 1?
No.
We can fix that. Did you have a question? Okay. So let me say this again. This was removable because the limit existed. Here, it's 1. This is non-removable because the limit did not exist. Now I'm going to go ahead and answer one more question real quick that was brought up on the, whatever that thing was we did at the beginning of class. The question is, why do we care? Well, there's 3 big ideas in calculus. One's limit, one's derivatives, and one's integrals. Guess what we almost always want when it comes to calculus to do either integrals or derivatives? Guess what we want the function to be? Continuous. We want it to be continuous. If it's not continuous, almost everything that we do in this class doesn't work. So why do we want to know if stuff's continuous or not continuous? Because if it's not continuous, we can't do differentiation on it. We can't do integration on it. By the way, if it's a removable discontinuity, can we fix it so we can do calculus on it? Yes, we can. If it's a non-removable discontinuity, guess what? We're out of luck. We can't do it. Does that make sense? Now, we haven't talked about derivatives or integrals yet, but that's why continuity is important. Okay? Okay, I think the next thing we need to talk about is continuity. I'm getting ready to erase both of these things. Are you guys okay with that? So I just asked you the difference between removable and non-removable, right? So now let's go with continuous. So I screwed up my picture now. I don't know if I can go all the way back here real quick. Trying to undo all the stuff I just wrote. Very inefficient, Mr. Allen. Ooh. Uh-oh. Did I screw up? Okay, I just want to get rid of that point.
That's because you drew these.
Yeah, you drew those after. So
Oh, I see. Okay, well, okay, so pretend that red dot's not there, okay? Can we just pretend that red dot's still not there? So here's what I want to ask. Let's see here. Okay, First of all, is the function continuous at x equals 0?
Yeah.
Yes.
Okay, good. So the answer is yes, I agree. So there's a point. Harder question. Why?
There's no gaps. Yeah, there's no holes.
There's no holes, there's no jumps, no, it's so good. So if you're in pre-calculus, I'd say good job. Unfortunately, you're no longer in pre-calculus. What's the calculus reason for why? Section 1.4, it's the fourth slide, just to let you know. You have to state 3 things. What are they?
One's a limit.
Number 1, we need to figure out what f of 0 is, and it has to exist. Number 2, Emily?
The limit of x equal to c of f of x exists.
Okay, so actually it'd be 0 in this case. Exists. And number 3?
And then limit as x approaches 0, f of x equals f of 0.
Correct. There are 3 conditions when you take your quiz in the future that you will have to answer to get full credit for why something is continuous. Number 1, you have to establish that the value of the function exists there, which kind of makes sense, right? If there's no point at that point, it can't be continuous. Number 2, you have to establish that the limit exists. Remember, if the limit didn't exist, that was a removal or a non-removable discontinuity. There's no way we can even fix that. So the point has to exist, the limit has to exist, and then number 3, guess what? They have to be equal to each other. All 3 of those conditions are required for this to be continuous. So what is f of 0? 2? Yep, I agree. F of 0 is 2. What is the limit as x goes to 0? It is 2. If I were ants on that curve and I'm getting closer and closer to 0, what y value do they appear to be going to? 2. Are these 2 things equal?
Yeah.
Therefore, continuous at x equals 0. By the way, these 3 dots means therefore. Have you guys seen that before? By the way, how many words did I use in my answer? Yeah, none, unless you want to count this one, which is an abbreviation for continuous. I'm telling you, when you do your assessments for me, if you tell me that there's no hole there, and that's why they're continuous, that's really nice, but you're going to get 0 points for that. That's not a calculus reason. I could go back into my Algebra 1 class and say, hey guys, is this continuous? And they'd all say yes. Hey guys, is this continuous? Or oh no. You need to give me calculus reasons for calculus questions. Okay? Here's the criteria. This is slide number 4. Slide number 4 on section 1.4. In fact, let's just talk about how to be successful in calculus. So if you go to module, the module for this week is right here. And we're going to go ahead and go to, oops, I just hit extra video. I don't want to watch the extra video. I want to do the notes for section 1.4, which are right here. So it's going to pop up. I apologize, guys. Most of the time when I put my notes in here, I make it to where there's 6 slides on one page. And here I accidentally forgot to do that, so it's like 20-some slides. But we're going to go to the 4th one, maybe, if it opens up. This is we're building suspense right now. Okay, so it's not going to come up, but can you just trust me that the 4th slide talks about the continuity? Is it coming? Let's see. Okay, there we go. 1, 2, 3. So, how did I know the definition for continuity at a point? It's in the notes. It's in the video. I went over it in the video. You want to do well in the class? The stuff that's in boxes like this, make sure you're familiar with it. I'm telling you, this one right here for sure will be on the next quiz. For sure. I will ask you some question about why is it continuous there? Just like I might ask you, why is it a non-removable discontinuity? Okay, I have one more thing about this section that I want to bring up. So let's do that, and then I'll have you guys do some practice problems. I'm going to go back to this. I'm going to erase the. Are you guys okay if I erase this? So here's my question now. Last question, and then I'll have you do some on your own. Why is the limit of f of x as x goes to 0 2? And let me preface this with, I would like a calculus answer, not because of the ants were walking closer and closer. That's kind of intuitively how we think of it. What's the calculus? Why is this? How? Let's say on the quiz I said, prove to me that the limit of f of x as x goes to 0 is 2. Maybe prove isn't the right word. I'll give you a hint, this is also in the notes. So here's the thing, when I ask you questions like this in class, it took mathematicians thousands of years to figure this stuff out. So if I ask you a question, if you're not thinking about a definition or a theorem or something that we've done in the notes, you're probably not going to come up with this on your own, no offense. It took them a long time to figure it out. And I'll be honest, I wouldn't have figured it out either. Why is the limit of f of x as x goes to 0 2? How would you justify that? Nope. Would you like, should I just tell you? Okay, here we go. So why, and I'm going to kind of go upside down here. The limit of f of x as x goes to 0 minus is equal to 2. What does that minus mean? By the way, if you haven't watched the videos, you have no idea what I'm talking about right now. That's why you're at a disadvantage. Because now you're basically, you might as well not watch the videos, I guess. What does that mean? What's that minus mean? It's going to be a long semester, folks. James?
It's like the left side of the.
Correct. It is the left-sided limit. So your lesson today, section 1.4, is continuity and one-sided limits. You were supposed to already have watched this. This is a fancy way of saying if the ants get closer and closer to 0 from the left side of 0. So that'd be like negative 0.01, negative 0.001, negative 0.00001. You see what I'm saying? So if the ants are coming in from this side on the, you agree, that's the left side, right? Correct? I shouldn't say right. Would you agree the ants are going to 2? So does this make sense?
Yeah.
Okay, so that's number 1. Can you guess what number 2 is going to be? Limit of f of x as x goes to 0 plus. If the ants are coming in from the right side, is it 2? Can you guess what number 3 is? These two are equal, right? Why is the limit 2? Because the limit on the left is 2, the limit on the right is 2, and 2 is equal to 2. Does that make sense?
Yeah.
By the way, how many words did I write there?
No.
a 0. Let me do one more here. Let's do 5. What is the limit as x goes to 5 from the left in my poorly drawn diagram?
3.
That's horrible. I know. Can we just say 3? I know that's bad. It kind of looks like it could be 2, but can we just say it's 3?
Yeah.
Okay. What's the limit as x goes to 5 plus
4.
4? So therefore, what is the limit as x goes to 5?
Does not exist.
Why?
Because they don't equal each other.
Correct. Doesn't that make sense?
Yeah,
By the way, did you learn anything yet?
yeah.
It makes sense, doesn't it?
Yeah.
So what I'm doing is, this is why I want you to write down your answers. Because you guys need to know how to write these things, because when you take the AP exam, that's what they're going to require you to do. They don't want you saying because there's a hole. They don't want you saying, well, if the ants come in from the left and the ants come in from the right. They want you to write stuff like this. By the way, you can see now why that's true, and you can see why that's true. It makes sense. These guys are going to the same value, so the limit existed. These guys are going to different values, so they did not exist. All right, so I'm going to pause now and let you guys. Okay, so I'm going to actually kind of use section 1.3 here a little bit and a little bit of section 1.4. The question is, does this function, is it continuous or discontinuous, and where so? And this is actually something that they teach you in Algebra 2. So they teach you about holes and asymptotes in Algebra 2. Did you know that? You used to know about vertical asymptotes and holes. So what I'm going to do here is, let's look at x squared plus 2x minus 24. And let's look at x squared minus 36. Now you guys would agree that that's the same thing as x plus 6 and then x minus 4 for the first one. I could factor it, right? And then here, if I factor this guy, you guys probably already know that it's x plus 6 and x minus 6. So what I'm saying is that this function is the same thing as x plus 6, x minus 4 in the numerator, and then x plus 6, and then x minus 6 in the denominator. Agreed? So I claim, by what I've done right here, we are interested in when the denominator is 0. Wherever the denominator is 0 is where we're going to have discontinuities. Who can tell me what x values are going to produce discontinuities in this picture? 6 and negative 6. So I'm telling you, therefore, we are going to have a discontinuity at x equals 6 and negative 6. Fact. Can anyone tell me what kind of discontinuity we're going to have at negative 6? So now we don't have a picture.
No, that would be
X equals negative 6 is removable. This is a removable discontinuity. Anybody want to tell me? No, you don't have to, this time you don't have to give me a calculus reason. Why is it removable?
because it's a whole
Right, but why?
because you can take it on top.
Because it
Yeah, there's no
cancels.
gap.
Yeah.
That's why it's removable. And I'm telling you, if you were to look at the graph, if you're not careful, if you look at the graph, you won't even see the hole. But if you zoom in, or if you look at the table, you'll see that it's an error there. Okay, good.
Why is
Hold on. What about at x equals 6? What kind of discontinuity is that? That is a non-removable. Why is that one non-removable? Did it cancel? Nope. Guess what it makes in the graph? You guys ever seen that word before? It's going to make a vertical asymptote. It's going to go to negative infinity and to positive infinity. So the limit on the left is going to go to negative infinity. The limit on the right is going to go to positive infinity, which is D and E. The limit is D and E. So the limit doesn't exist. That makes it non-removable. Did I just answer your question? Now, guys, I'm going to throw out one more thing just in case, because sometimes if I don't say this, students will start making stuff up. Why have I not talked about x equals 4 in this problem? Because it's on top, because it's not in the denominator. It's not going to make any kind of discontinuities. We're only interested in fractions. We're interested in the denominators. Okay? All right. So, I mean, if you got a second, graph this function. And let me make sure I make something very clear. In fact, I should do this right now. Let's just go ahead and look at this. So f of x equals x squared plus 2x minus 4 over x squared minus 36, right? We said that that's essentially the same thing as x minus 4 over x minus 6, right? Now, I want to make sure I'm very clear on this. I'm going to call this the f function, and I'm going to call this guy over here the g function. Are the f function and the g function the same function? They are not. Guess what this one has that this one does not? It has a removable discontinuity. It has a hole. This one does not. Does this one have a vertical asymptote at 6? Yes. Does this one have a vertical asymptote at 6? Yes. Does this one have a hole at negative 6? Yes. Does this one? It does not. So if you look carefully in your notes in section 1.3, they'll talk about how to find the limit of two functions that are exactly the same except for one point. And by the way, the only point that these two guys are different is that removable discontinuity. We removed the discontinuity. We could not remove that asymptote. We could remove the hole. We could not remove the asymptote.